Dear students, in coming section we are going to discuss few important illustrations, and through coming illustration we will learn the application of the important concept of the rotational dynamics. So let us take illustration number 1, and through illustration number 1 we will learn the application of the torque equation. Second point, we will discuss how to write the constant equation in the rotational dynamics, and third point, we will discuss analyzing object in the combined rotation and translation. Okay. So first illustration is this, you can follow the screen. Given question is the system shown in the figure. You can observe this figure is having a block and hanging disc. This block is placed on the smooth horizontal surface, that is, there is no friction between the block and this surface. And the motion of the disc is the combined rotation and translation. We know the center of mass of disc will move in the vertical downward direction, and disc will rotate about the center of mass also. So the motion of the disc is the combined rotation and translation. This pulley is small, right? This is massless. That means we can neglect the moment of inertia of this pulley. That means the string will slide over the pulley. That means we can neglect the rotation of this pulley. So let us do one thing. Let us make the diagram to the next page here, right? The first and foremost important thing is drawing the free body diagram. So here first we are going to draw the free body diagram of the block and disc. First analyze the block. We can observe here block is having the three forces, that is the weight mg, normal reaction upward direction, and tension force acting on the block in the rightward direction, right? This is mg, this is the normal reaction. Normal reaction is a pushing force that is acting toward the block, and tension is a pulling force that is acting away from the block, this one. Now consider the disc. Disc is having the two forces. One is the weight, gravitational force. Second is the tension force acting in the upward direction, like this. This is the weight, and this is the tension force, right? We can observe here, if we consider the center of this disc and we consider the torque acting on the disc. So the torque of the weight will be 0 and torque of the tension will be in the clockwise sense. That means the rotation of the disc will be in the clockwise sense. So let us assume the angular acceleration of the disc as alpha. This is alpha, right? Now consider, we know the motion of the block is translational. So let us consider the acceleration of the block. So acceleration of the block, let us assume this as a small a, right? And acceleration of the center of the disc is small b, right? This one. Now let us consider a point on the rim of the disc. Let us say this point is P here, right? So this is a point P. We can observe here through point P, string is moving in the upward direction and finally connected to the block. That means this point P is directly connected with the block. That means the acceleration of the block magnitude wise will be same as the acceleration of the P, and it should be in the downward direction, because we know as this block will move in the rightward direction, there will be the shifting of the string in this section, and that means P point will move in the vertical downward direction. So we can say the acceleration of the point P will be the same as the acceleration of the block, that is a small a. So we can say the acceleration, this is a small a, right? Now we can write the vector equation of acceleration of point P. We know point P is a part of the disc, and disc is having the motion combined rotation and translation. That means we can write the acceleration of the point P as acceleration of the point P with respect to O, that is the center of the disc, plus acceleration of the O. This is the vector equation. And here we can observe here the rotation sense of this disc is in the clockwise sense. That means the acceleration of the P with respect to O will be in the upward direction, and magnitude will be equal to R alpha. We know this acceleration is the tangential acceleration. So R alpha will act in the upward direction, and acceleration of the center of disc, that is acceleration of O, is acting in the downward direction. That means net acceleration of the point P should be the resultant of B and R alpha. And because this point P is moving in the downward direction, so let us take downward direction as positive. That means we can write small a equal to B minus R alpha, or you can say this is equal to A, this is equal to minus R alpha, and this is equal to B. We can rearrange this equation. We can write here this B equal to R alpha plus A, or A plus R alpha. This is the acceleration of the center of the disk. Okay. Now let us consider the free body diagram of the block again. We know this block is in equilibrium in the vertical direction. That means this normal reaction will be balanced by the weight. So here we can write the vertical equilibrium of the block, that is N equal to mg. Okay. Now let us consider the horizontal direction of this free body diagram. In horizontal direction there is an unbalanced force, that is capital T, and we know any unbalanced force should be equal to mass multiplied by acceleration of the object. That means T equal to mass of the object, that is the mass of the block, multiplied by acceleration of the block. That means we can write T equal to m multiplied by A. This is the horizontal force equation, equation number 1. Okay. Now let us consider the vertical direction or vertical motion of the disk, right? Vertical forces acting on the disk is mg in the downward direction and T in the upward direction, but we know the center of disk is moving in the downward direction with the acceleration b. That means we can write the net forces acting on the disk equal to mg minus T, right? This should be equal to mass of the disk multiplied by acceleration of the center of disk, that is b. So this is equal to mg minus T equal to mb, right? Now we can substitute the value of b. This is equal to A plus R alpha, right? So this is equal to, and T also we can write ma. So this is equal to mg minus ma equal to m multiplied by A plus R alpha, right? Here we can cancel out small m and small m, right? Like this we can cancel, and this equation finally become R alpha equal to, A will move to this side, that is equal to G minus 2A. So this is equation number 2. Let us do one more thing. Let us write equation number 1 and equation number 2 the next page. This one, equation number 1 and equation number 2. Okay. Now we can apply the torque equation. And about the torque equation, one very important thing is it is applicable either about center of mass or about a fixed point. There is no fixed point on the disk because this is moving. That means we can apply the torque equation only about the center of the disk. So let us apply the torque equation about center of the disk or about the centroidal axis. Okay. And this torque equation we know this equal to torque equal to I multiplied by alpha, and I is the moment of inertia about O. So we can write now this torque equal to I alpha, and this torque equal to T multiplied by R, right? Tension multiplied by radius, and I is the moment of inertia about O, alpha is the angular acceleration. And we know the moment of inertia of the disk about O, that is about an axis passing through O and perpendicular to the plane. So this is equal to mr square divided by 2. So we can write in place of I not equal to mr square divided by 2. Now here also we can observe this R and this R will get cancelled. So here we have the equation T equal to mr divided by 2 multiplied by alpha, or you can say 1 by 2 mr alpha, equation number 3, right? Now we can do one more thing. We can substitute the value of T in this equation, T equal to ma and R alpha equal to G minus 2A. So we can substitute the value of R alpha and T in equation number 3rd, like this. Okay. M and M again will get cancelled. This and this will get cancelled. That means now we can solve. This is 2A equal to G minus 2A. That means 4 is small a equal to G. That means A equal to G by 4. This is the acceleration of the block. This one. Now we got the acceleration of the block. Again we need to calculate the acceleration of the center of the disk, and center of the disk is written as this B equal to A plus R alpha. We got the value of A, we know the value of R alpha equal to G minus 2A, and here again we can substitute the value of A. So let us move to the final concluding part. So let us write B equal to A plus R alpha, and A equal to, we have calculated G by 4, and R alpha equal to this one. So let us substitute the value. So acceleration of the disk will be this one. Now we can solve, right? We can substitute the value of A again, that is G by 4. So we can now finally solve the equation, and it is equal to 3 G by 4. That means acceleration of the center of disk will be equal to 3 G divided by 4. So in previous illustration, what we learned? First we learned how to write the torque equation. Number second point, how to write the constraint equation, and the motion of the disk was the combined rotation and translation. That means we discussed 3 important points of the rotational dynamics. Now let us take one more illustration, and through coming illustration we are going to analyze the motion of the object under combined rotation and translation. And second point we will discuss, that is the identification of the location of the instantaneous center of rotation or instantaneous axis of rotation. And third point we will cover application of the torque equation. And fourth important point, we are going to discuss the analysis of the cases of overturning. So let us move to the illustration part. You can observe here in this diagram, this block of mass is small m, height is small h, width is b. You can consider this as a square base of width b. It is placed on the rough horizontal surface. This is a rough horizontal surface. A thread is attached to the middle point of the right top edge. This is the middle point of the right top edge of this block, and a string is connecting this point to a disc. You can observe here the mass of the disc is also a small m, right? And this disc is a small disc, or pulley is a small disc. There is no mass is given, size is also not given, it is a small. That means we can neglect the rotation of the pulley. That means we can consider the string is sliding over the pulley. That means we need not consider the moment of inertia and other thing for this disc. We need to consider only this disc, because this is having the combined rotation and translation. And in question we need to calculate the minimum required coefficient of the friction mu between the block and horizontal surface, so that it can remain in the static equilibrium. That means this block is not moving, this is at the static position. That means we can consider this point as a fixed point, right? So let us do one thing, let us place the diagram, and one more thing we need to calculate here. It is given the minimum possible value of B, the minimum possible value of this base. Okay. So let us place the diagram to the next page here. In very first step, let us calculate the position of the instantaneous center of rotation. The question arises, what is the instantaneous center of rotation or instantaneous axis of rotation? Instantaneous axis of rotation is the axis. About that axis we can consider the rigid body is rotating at that instant. That means the position of certain point about the whole body is rotating, that point is called the instantaneous center of rotation. The requirement of the instantaneous center of rotation is the point should be rest at that moment. That means velocity of that point and acceleration of that point should be 0. So let us explore which point is having the velocity 0 and acceleration 0. We can observe here this block is not moving, and this is a fixed point, and this string is connecting this fixed point to this point. So let us make the enlarged view of this disc like this. That means this point is not moving at this moment, because this is a fixed point, it is not having any moment. That means with respect to ground, the moment of this point will be 0. The velocity is 0, acceleration is 0. Let us call this point as A, right? Now we can consider the total a rigid body, the whole rigid body, or here in our case is the disk. The disk is rotating about this point. That means the disk is performing the pure rotation about A. And sense of rotation, we know, if we place a hinge here, the disk will rotate in the clockwise sense, because mg is acting in the downward direction, the torque of the tension will be 0. That means rotation sense of the disk will be clockwise, like this. This is the ICR and this is the rotation sense. And rigid body is having one important property. The rotation sense on rotation parameter is same for all point. That means if it is rotating in the clockwise sense about this point, about center of the disk will also rotate in the clockwise sense with the same angular acceleration about this. So, let us write the angular acceleration of this as alpha. This is the angular acceleration, right? We can say the center of this will also perform the pure rotation about A. The radius of rotation is r and angular acceleration is alpha. That means acceleration of the center of this will be alpha multiplied by r in the downward direction, like this. So, we got the acceleration of the center of the disk. Okay. Now, let us draw the free body diagram. Free body diagram, if we consider this disk, we have the two forces, one mg, that with the weight of the disk act in the downward direction. Second force is the tension force, that will act in the upward direction passing through A. This is the free body diagram, right? And if we draw the free body diagram of the block, this block will have the three forces, majorly we can say three forces, and one more force here also, of course, that is the friction. That means we are having the four forces acting on the block. One is the weight, that is mg, downward direction. Second, tension force is a pulling force that will act from this point, that the middle of this as T will act in the rightward direction. Normal reaction will act in the upward direction, right? And friction force will be static of nature, that will act in the backward direction. Say this is small f. This is the friction force, right? Now, we can write the torque equation. As we discussed, torque equation is having very much limitation. It is applicable about the centroidal axis first, and second about a fixed point. So, we can apply the torque equation about the center of mass or centroidal axis, and we have one more point, that is the ICR, that is a momentary fixed point. That means we can apply the torque equation about this point also. That means we are going to apply the torque equation about A. And let us explore how many forces are acting here. Tension passing through A, that means the torque of the tension force will be 0, and torque of mg will be equal to mg multiplied by r. And we know torque equal to I alpha, and torque will be equal to mg multiplied by r, and I is the moment of inertia about the rotation axis. Rotation axis passing through A, that means we need to write the moment of inertia about A. So, we can write here mg multiplied by r equal to Ia multiplied by alpha. Okay. And moment of inertia, regarding moment of inertia, we know that this is a disk having the moment of inertia mr square divided by 2 about an axis passing through O and perpendicular to the plane. We can apply the parallel axis theorem to get the moment of inertia about A. So, we can write moment of inertia about A equal to Ia equal to, this is mr square divided by 2 plus the distance of the point under consideration to the axis of rotation is again r. So, we can write plus mr square. So, this is equal to 3 by 2 mr square. We got the value of Ia. We can substitute the value of Ia here. So, we got the equation 3 by 2 mr square multiplied by alpha, right. We can observe here small m and small m will get cancelled, capital R and capital R will get cancelled, this R and this R will get cancelled. Here we got the equation, this is R alpha equal to 2 by 3g. This is the value of R alpha. R alpha is nothing but acceleration of the center of the disk. So we got the acceleration of the center of disk. Now we can apply the force equation for this disk, and this center is moving in the downward direction. That means the force equation will be equal to mg minus t, that is the net force acting on the disk, that will be equal to mass of the disk multiplied by acceleration of the disk. This is nothing but R alpha. So let us write the force equation for the disk, right? And here we know this R alpha equal to 2g divided by 3. So we can substitute the value of R alpha, right? Now we can find the value of T, that is the tension on this string. So this T should be equal to mg minus 2 by 3 mg, that is T equal to 1 by 3 mg. This is the tension, right? Now we can consider the free body diagram of this block. This block is at static equilibrium. That means in horizontal direction net forces acting on the block should be 0. That means T should be equal to small f, that is the friction force. That means the friction force, that is a static nature, that is equal to 1 by 3 mg. So let us write small f equal to T equal to 1 by 3 mg. This is the free body diagram of the block. So we got the friction force, and we know this block is at static equilibrium. That means static friction, and if it is static equilibrium, we can write F equal to mu multiplied by n, because we need to calculate the value of small b. It is given the minimum possible value of small b. For minimum value of small b, the friction force should be maximum. That means the value of small f should be equal to mu multiplied by n. So this friction force should be equal to mu multiplied by n. Now we can substitute the value of small f equal to, this is 1 by 3 mg. So let us write 1 by 3 mg and n equal to small mg. We can observe here small m and small n will get cancelled, and here mu is equal to 1 by 3, right? This is the minimum possible value of mu. So this is the minimum possible value of the coefficient of friction for this block will be at static equilibrium, right? But let us observe this free body diagram again. What happens if we increase the value of T? Small f will also increase, and this value will keep on increasing up to this small f is equals mu multiplied by n. But up to that point, capital T is equal to small f. That means you can observe a couple is acting on this block, and the value of the couple is equal to T multiplication small h. Small h is the height, because the separation between these two parallel forces is a small h. And this couple is try to rotate this block in the clockwise sense. That means if we increase the value of capital T, this block is having the overturning tendency or toppling tendency about the right lower edge, right? That means this overall body, or you can say this block, will start rotating about this axis. That means the base of the block will leave the ground and will be situation like this, somewhat like this, right? The base will leave the ground, you can observe, and this just lift and start rotating about this. That means the normal reaction will pass through this point, mg, as it is passing through the center of mass, and normal reaction as we discussed from here, and friction force, that is the static nature, will act in the backward direction, right? And toppling tendency as we discussed, because of this couple is in the clockwise sense like this. And here what tension force is doing? Tensor force is toppling the block, and mg, the torque due to the mg, is restoring the block. That means for stopping the overturning, or we can say if we want to prevent the block from overturning, the restoring torque due to mg should be greater than the torque due to capital T, or you can say the torque due to capital T is less than or equal to restoring torque due to mg. And torque due to capital T is equal to, about this point P, is equal to capital T multiplication small h, and torque due to mg is equal to mg multiplied by the lever arm for mg is equal to B by 2. So we can write here T multiplied by small h is less than equal to mg multiplied by b by 2. We can rearrange here. We can write this b value is equal to, and we got the value of t, and t is having the value here we have calculated, that is equal to mg divided by 3. So, we can substitute the value of this is equal to mg divided by 3. Finally, value of b will occur as 2h divided by 3. And we know the value of a small h that was 15 centimeter. So, this is 15 multiplied by 2, 30 divided by 3, that is equal to 10 centimeter. That means size of the base should be 10 centimeter, right? Minimum size of the base should be equal to 10 centimeter. If we decrease the size of the base from 10 centimeter, this object will overturn or topple about this edge. Okay.